Okay, so these are going to be standard deviation notes to go with the enzyme catalase lab, but you can use them actually for any lab that you do. Right now what I have up is the AP Biology equations and formula sheet. You should have a copy. This is the copy that you will, or this is a copy of what you will actually receive on an AP exam, but this is what you can also use for the lab. Now I'm using Explain Everything, so I'm not completely familiar with it. If there's any errors as I'm going through, I'll try to fix it as we go, but I'm a little clunky, so please be patient. So the formula that you're going to use here is going to be this one right here, the standard deviation right there, okay? And so, let me see if I can move this over here. I'm going to actually shrink it down here so I can see it. And I'm going to give some data here. This is just going to be, let's see. This is just going to be some data, pretend data that we're using. So I'm going to pretend that our data, that we ran the enzyme lab 4 times. And time number 1 here, or trial number 1, my rate was 0.8. Now I'm not comfortable writing with my finger, so I don't have my labels up here, but we'll say 0.8 milliliters per rate. So this is the actual rate. I can do this. Okay. For number 2, let's say it was 0.3. For the third one, let's say it was 0.7. And for the fourth trial, it was going to be now let's do a big high one, 1.2. Okay. Oopsie. So we have 0.8, 0.3, 0.7, and 1.2 as our data set, okay? And so what you would do is it's kind of like a plug and chug. Right there, our standard deviation is a little e. That little e is going to be sum of. So sum of xi is each individual data point minus x with the bar over it. X with the bar is equal to the mean. And it actually says it right up here at the top. Right there at the top. And so the first step actually is step 1 equals find mean. So if I were to add those 4 up here, and I have a calculator next to me, but if you want to take a calculator, do it in your head or on paper. 0.8 plus 0.3 is 1.1, plus 0.7 is 1.8, plus 1.2 is 3. I divide it by 4 because I'm adding 4 together, so my x minus equals 0.75, okay? 0.75. So I'm going to use that every time that I use, every time that I need to subtract x with the bar over it. Okay, so I'm going to flip to the next page here. Let's see if this works out. Oh, it didn't save it. Actually, where it was a little bit emptier. I figured out my standard deviation. I plugged and chugged, and I have 0.37. Now, when you are graphing your data, let's say you have a bar graph, that you're using a bar graph to plot just the average of that trial. And so the average of that trial was 0.75, right? So we'll have like 1 here, 0.5 here, okay? So it's 0.75. What that means is that if we were to graph the error bars using standard deviation, we could be fairly confident that if we add 0.37 up and 0.37 down, we would have 75% of our data. Actually, I don't know why I just said 75%. Let me see if I can just undo it. It's 67%. I think I was thinking the 0.75 here. 67% of our data. And if we were to go up another 0.37 and down another 0.37, we'd have 99% of our data included. And so that's what that's telling us. When you are doing the write-up, you're going to think of it as just reference it in terms of how spread out it is. I am confident that 67%, so you would write it as in something like this. Let me see. Whoopsie. Let me see if I can do this. We are statistically, because we're using statistics, that 67% of the data, or times that enzyme rate is measured, it will fall between, and I'm not sure how to do plus minus on this, but you know the little plus with the minus on it, 0.37 milliliters over minutes of the average 0.75. That shows them how kind of the range, if someone else is reading your lab report, they will now have a range that they know that your data fell into. And so you can display it on a graph with the bar or a data point, and then the lines, the bars that come off of it. And then that's kind of how you would translate it into your lab report. So I hope this helps. I know explain everything's a little bit clunky, but with trying to write out and show you guys stuff at the same time, I didn't know a better way to do it. Please let me know if you still have questions. There are plenty of tutorials. If you Google standard deviation tutorials, you can get plenty of other videos that are out there too. Okay? So I'm going to go ahead and put this away. Stop this. So remember that x equals 0.75. X, the mean. So I take each individual data set, and let's see if I can move this. Oops, I don't want to move the whole thing closer. I just want to make it so I can move that a little bit bigger. Okay. Let me see. There we go. So you guys can see it a little bit better. Okay, so what I'm going to do now is step 2. For each one, I'm going to take each individual value minus the mean, and I'm going to square it. And the reason I'm squaring it, I'll show you why actually in a minute. So I'm going to have to actually go back and forth. Let me see if I have it on my calculator here. So the first one that I had was 0.8. So I have 0.8 minus 0.75 equals 0.05. And I'm going to go ahead and square that here. And 0.05 squared is going to be 0.0025. The next one I had, I believe, was 0.3. Again, I'm going to minus 0.75, the mean, and that is going to give me negative 0.45. So this right here is why I'm doing, why I'm squaring all the values to begin with. Because if I get a negative sign and I try to go ahead and add it together, it's going to start canceling out the positives. Remember, standard deviation, you're measuring the variance of either the population or the sample depending on what you're using it for. In the case of the enzyme catalase lab, we're actually finding out the variation from the mean for the trials that you did. And so we want to see you did 3, 4, whatever different trials. We want to see how spread out your data was or how close together. The larger the standard deviation, the more spread out your data is, and perhaps the less precise. Remember, precise means that you're going to get the same results over and over. A low standard deviation will indicate that your results are more precise. And so it gives us this idea of confidence, the confidence that we're using, that we can take our results in our conclusion for. So what is our confidence when talking about our data? How reliable is it? And so to get an accurate representation, we're going to square each of these distances from the mean that each of these points are. We'll go back through at the end and we'll undo the squaring that we did by finding the square root. But that's a little bit of background on it. So the third one was 0.7 minus 0.75 again. Now we have a negative 0.05, but it's still going to be 0.0025 that we're interested in. 0.0025 that we're interested in. And you know what? I don't know if I actually ended up squaring the one from the negative 0.45. The negative 0.45, and if I had squared that one, I'm sorry, guys. Is 0.2025. So let me do this. That's for the second one. Up here it was 0.0025. 0.0025. I know I'm writing over numbers. Sorry guys, I'm trying to keep all this stuff on the same page though. And then our last one was 1.2. I might have mixed these around, but same idea. Minus 0.75. 1.2 minus 0.75 is going to give us 0.45. Oh, that's funny how that happened. We already figured out that negative 0.45 squared was 0.205, and so this one will be 0.2025 as well. 1.2 minus 0.75 was equal to 0.45. When we squared it, we got 0.2025. Okay, so as I am unsure, how do I lock this? To lock this, is this how I lock it? When to lock. Hopefully it will lock everything here. I'm going to go on to the next page. So I'm actually going to be, just joking, I'm actually not going to be able to go on to the next page because it looks like I have to use what I've set up because I've only gotten 2 pages set up. So what I'm going to do now is I'm going to erase this, you guys, just so I have room. I think, nope. So I'm erasing this. I know there's got to be an easier way. I'll play with explain everything later, though, to find out more features. Right now, I just want to give you the standard deviation part. So what I'll do here is I am going to go back and I'm going to add in my 4 values. Remember, I'm on this, well, actually, the step that I'm on here is still figuring out the top of the standard deviation. So I'm going to sum it. Sorry, my little E, my sum sign is kind of falling off. So I am going to sum those 4 numbers that I just got in green. I'm going to sum 0.0025, 0.0025, 0.2025, and 0.2025. And if I sum those 4 digits together, I have 0.41. So this gives me the top of my equation for my standard deviation, 0.41. So now I'm into S equals square root of 0.41 over n minus 1. So n minus 1, that's going to give us the confidence. Now n is going to represent the number of trials. So n is 4 data points, minus 1. So 4 minus 1 equals 3. So S is going to equal square root of 0.41 over 3, which equals square root of 0.41 divided by 3 equals 0.137. I go ahead then and I take the square root of that answer. I'm going to put it right up here. And my final answer will be 0.37. Okay, so 0.37 is my standard deviation. 0.37 is my standard deviation. And so the idea here is, okay, now what am I supposed to do with that? And so let's go, I'm going to go back to the